So we're studying power series, and we're really looking how a power series. We're looking at how a power series can approximate a function, and actually, a power series can represent a function on its interval of convergence. And so, it's really important for us to find the interval of convergence and the radius of convergence given a power series. So let's look at this power series. So this power series. Notice that what we've been using is the ratio or the root test to test for absolute convergence. And once we do that, we can find the interval of convergence. Now, I think we looked at this example, but let's look at it again. And first of all, notice that the center of the power series is 2. All right, so here we go. Let's use because everything is being raised to the power of k, that kind of leads me to the root test. So let's use the root test now. All right, so this is the root test. And here, remember that if, I know it looks like the letter P, especially the way I wrote it here, but it's really the Greek letter rho. RHO, rho. Anyway, but that's not important. But we do know that if rho is less than 1, then the series converges absolutely. But if rho is greater than 1, then it diverges. If it's equal to 1, it's inconclusive. All right, so this here, we know that the kth root of the kth power are inverse operations, right? And so they cancel. So anyway, you're left with the absolute value, well, hold on, the limit as k goes to infinity, and excuse my sloppy writing, of the absolute value of x minus 2 over just 4. So what we know is that this power series converges absolutely as long as this value here, this expression, is less than 1. So what we do then is we take this expression and we make an absolute value inequality, really, and we say that this series will converge absolutely as long as this is true, right? And so in order to solve this for x, we write this absolute value inequality as a double inequality here. We're going to multiply everything by 4 and there, and then we're going to add 2 to everything. So when we add 2, then we get the interval of convergence, which is -2 between -2 and 6. All right, so far we know that the interval of convergence is from -2 to 6. But what we still need to do, though, is we need to test the endpoint. So what about at 2, what about at -2, and what about at 6? Does the power series converge at the endpoints? Now, it can converge at one endpoint and not the other. It can converge at both endpoints, or it can converge at neither of those endpoints. All right, so that's what we need to do, is to figure out. Now, the way we're going to do that is we're actually just going to plug these endpoints into our power series one at a time and investigate. So here's our series. What I'm going to do is I'm going to plug -2 into the series and investigate. All right, so when I do so, I have this. Plugging in -2. Okay, what I want us to consider is, when k is equal to 0, this is -1 to the 0th power, which is +1. When -4 is raised to the 0th power, this is +1. So this is positive. All the numerators positive. When And now what I want us to do is plug in the right endpoint and see what we get. And I think we get the same thing. Okay, so plugging in the right endpoint, positive 6, into our series gives us the following, 4 to the power of k over itself is just 1. So all you're left with is negative 1 raised to the kth power. Now this diverges by the divergence test as well. I mean, you can see that this is going to continue to oscillate. So this series here, the limit is not equal to 0. So once again, this diverges by the divergence test. So therefore, this interval of convergence, I mean, it is what it is. Keep the parentheses on both endpoints there. And then, if it helps, this is what we're saying, the center of our series is 2. We said that at the very beginning. And the interval of convergence is between -2 and 6. So therefore, this here is what we call capital R. So is this distance is here as well. So we know that the radius of convergence is 4 units. So this would be our final answer right there. Okay, let's look at a new series. All right, here's our new power series. Notice that the center is 0. Let's use the ratio test here. I do have a mixture between a combo between factorials and the power of k. So let me not use the root test. Maybe let me try the ratio test. All right, here's the ratio test. All right, and I'm going to start simplifying here. There we go. All right, so we know that x to the power of k plus 1 divided by x to the power of k is just x. So I'm going to have the absolute value, of course, of x. And now k plus 1 factorial divided by x, k plus 1 factorial divided by k factorial is just k plus 1. And what I'm going to do is I'm going to factor out the absolute value of x like this, all right? So then this is just the limit as k goes to infinity of k plus 1. Now, this is equal to infinity, right? So this entire limit is equal to infinity, which is, by the ratio test, this value, this limit is absolutely greater than 1. Infinity is greater than 1. Therefore, this power series diverges. Now listen to this. This power series can only converge if this limit is less than 1. But notice that it's not less than 1. It's greater than, it's infinity. But the only way that this limit could be less than 1 is the one and only case where x is equal to 0. If x is equal to 0, then this entire value is 0, which is less than 1. So therefore, this power series converges only at this value, only when x is equal to 0. So therefore, we're going to say the interval of convergence is just the set 0, okay? And that means since the power series is centered at 0, the radius of convergence is just 0. Okay, so this is good. Let's look at one more power series. My initial thought for this power series, by the way, it's centered at 2, okay, centered at 2. But my initial thought here was to use the root test because I saw this power of k here and I don't see any factorials. So I was thinking the root test. But then I came to realize, this is not raised to the power of k. It's a square root of k. So I changed my mind. Let's do the ratio test here. Okay, I have my ratio test all set up. So let's start to simplify, okay? All right, so then this is the limit as k goes to infinity, of course, of, let's see, x minus 2 raised to the power of k plus 1 over the square root of k plus 1 times the square root of k over x minus 2 raised to the power of k. I'll get rid of my absolute values in the next step, maybe. All right, so let's continue to simplify. So then this is equal to the limit as k goes to infinity. Now, x minus 2 raised to the power of k plus 1 divided by x minus 2 raised to the power of k leaves me with just x minus 2 raised to the first power. But I still need absolute values around that. And then as far as my expressions involving k here, I can use the quotient rule for radicals to say that this is equal to the square root of k over k plus 1, like that. I'm going to pull out the absolute value expression because it doesn't have k in it at all. So it's the absolute value. Let me fix that, make it cleaner there. Okay, so we have the absolute value of x minus 2 times the limit as k goes to infinity. There we go, of the square root of k over k plus 1. Now, this is equal to, this limit here is equal to 1. You can use L'Hopital's rule, or you can just divide the numerator and the denominator by, technically, by the square root of k. And you're going to get 1 over 1 plus 1 over k here, or the square root of k. And anyway, so this here is equal to 1. So then I have just this, okay, because this is equal to 1. Okay, so then we know that the power series converges absolutely only when this expression is less than 1. Solving for x, this implies that negative 1 is less than x minus 2, which is less than 1. Adding 2 gives me that my interval of convergence is between 1 and 3. Awesome. The only thing that's left to do is to test the endpoints. So what about at 1? What about at 3? We're going to plug those values into the power series and investigate. Okay, I've plugged in 1 into my power series, and this is what I get. This is an alternating series. You know, negative, positive, negative, positive, negative, positive. It's an alternating series, and we know that an alternating series, by the alternating series test, converges absolutely, as long as the magnitude of my terms is non-increasing. And that's true because the numerator is going to be fixed while the denominator, it continues to grow without bound. So in other words, these values are actually decreasing. So that's one thing. The second thing is that we need to show by the alternating series test that the limit of the sequence, or the series rather, is 0, and it is. So the alternate series test, because both of these things are true, we know that this converges absolutely. So that tells me that I'm going to actually put a bracket on 1, because 1 is actually included in the interval of convergence. It actually converges at 1. All right, let's plug 3 in now and figure out what we have. All right, when we plug 3 in, we just get positive 1 to the power of k, which is just 1, and then over square root of k. This is a divergent p-series because the power on k is 1/2, which is less than 1. All right, so then we just confirmed that 3 in the interval of convergence is not included, but the left endpoint is. So really, this is like a picture of what we have, all right? So here's my, remember that the series is centered at 2. So then this is really what we have. Here's the center, and we have 1 is included, but 3 is not. So of course we would write it like this, and our radius of convergence is just 1 unit only. All right, cool. Okay, so this part is important. Now we're going to be given a series, and we want to differentiate it. We want to integrate it and find a new function. All right, a new series which represents a new function. All right, so let's do it. So look at this first series that's given to us. This function, this rational function, we've already seen, and we have it in our notes, that it is this series here, this actually geometric series, geometric power series, x to the power of k, which is 1 plus x squared plus x cubed plus x to the fourth. And this series represents this function for over this interval of convergence. So we already know that. So what we're going to do right now, we're going to answer part A. We are going to differentiate this series here and find a new function and a new series. All right, so let's go ahead and differentiate. Well, actually what I'm going to do is I'm going to differentiate both sides. So I'll differentiate the left-hand side. I'll differentiate this function. You can use the quotient rule, or you can use the power rule. The power rule will probably a little faster maybe, but I'm going to differentiate this left-hand side, and then when I'm done, I'll differentiate the right-hand side, which is this power series. All right, cool. Let's do it. So f of x is equivalent to 1 minus x raised to the power of negative 1. That implies that f prime is negative 1 minus x raised to the negative second power, and then by the chain rule times negative 1. So then this is equivalent to just 1 over 1 minus x quantity squared. Okay, so this, folks, is f prime. I differentiated the left-hand side. I differentiated my function. Now I want to differentiate the power series, and the way I do that is just by term by term. And what I'll do is I'll set this derivative equal to the derivative of the power series, because after all, they're equal, right? This function is equal to this power series. Therefore, the derivative of this function must be equal to the derivative of the series term by term, of course. All right, so let's do that now. Okay, so let me write it like this. When I differentiate the series term by term, of course, we get 1 plus 2x plus, the derivative of 1 is 0. The derivative of x is 1. That's why I put a 1 here. The derivative of x squared is 2x. The next term right here would be x cubed. The derivative of x cubed is 3x squared. The next term would be 4x cubed, and I think you get the idea. So plus, etc. So if this is f prime and all of this is f prime, therefore we can say that f prime, which is 1 over 1 minus x quantity squared, is equal to this power series, 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the fourth plus 6x to the fifth, and so forth, right? Which all of this, of course, can be written using, summation notation. So let me make a little more space here for myself. So then this is equal to the summation of, let's see, notice that all of the coefficients, so 2 and 3, and even the 1 here, is 1 more than the power that's on the variable. See, power 2, coefficient is 3. Power 1, coefficient is 2. Technically, it's x to the 0th power, and the coefficient is 1. So I know the coefficient will be 1 more than the power. So it can be written like this, k plus 1, and then x to the power of k, as k goes from 0 to infinity. Now, this derivative function can now be written as a power series like this. All right. And this is true on this interval. So we should add that. This is true for the absolute value of x is less than 1. That's pretty cool. Now, what we should check is -1 and 1. Because remember, the interval of convergence, this interval right here of convergence is, let me write it like this. It is this, right, everybody? So the endpoints of your interval of convergence are -1 and 1. If we plug -1 into this power series to check the convergence at the endpoints, you get -1 raised to the kth power, which is going to make this an alternating series. But you know what? The terms are not they're not non-increasing. They're actually increasing, right? As k goes from 0 to infinity, it's actually making this series oscillate. Okay, and so anyway, a point of the matter is this is not converging. It's actually diverging by the divergence test. So -1 is not included. Same thing goes for +1. When you plug +1 into x, you just get 1 to the kth power, which is just 1. And this is approaching infinity. So by the divergence test shows me that -1 and 1 are not included in the interval of convergence. So this is the interval of convergence between -1 and 1. Of course, you can write it like this if you'd like. -1 and 1. But you should always consider the endpoints. Always consider the endpoints to see if the interval of convergence includes or does not include the endpoints. Okay, let's look at another, actually, no, not another example. Let me go back up here. So this is, we just finished differentiating a power series, right, everybody? So now what we have yet to do is integrating our power series. So let me integrate this, and let me integrate this term by term. Okay, so what do we get when we integrate this? All right, let's go for it. Okay, integrating the left-hand side here, it'll be the integral of 1 minus x dx. You can use a u substitution here, but you and I know that you're going to get negative, by the chain rule, you're going to get, or by the u substitution, the opposite of, or the negation of, the natural log of 1 minus x. I forgot the 1. 1 minus x, like that, okay? All right, so this is the integration of 1 over 1 minus x. So we integrated the left-hand side. Now what I'm going to do is I'm going to integrate the right-hand side. Term by term, of course. So when I integrate 1 plus x squared plus etc., I get x plus x squared over 2 plus x squared plus x cubed over 3 plus x to the 4th power over 4, and so forth. So therefore, what I'm going to say then is, because of this equal sign up here, because this function is equal to this series, I know that the antiderivative of this function must be equal to the antiderivative of this. So in other words, I know that negative natural log of 1 minus x must be equal to x plus x squared over 2 plus x cubed over 3 plus etc. Let's not forget that because this is an indefinite integral, it's going to be some plus some number, some constant on the back end. Matter of fact, when you if you were to plug in 0 for x, you would get the natural log of 1, which is 0. So this entire left-hand side is 0. And if you plug in x equal to 0 on the right-hand side, you just get 0. And if we choose c to be 0, then this entire statement is true. Okay, so we're really letting c be 0, the constant 0, so that I don't have to write the c. Okay, in other words, what I'm saying is the negation of the natural log of 1 minus x, actually I can do away with the absolute values, because remember that we have, let me scroll back up here. For this series, we have that the absolute value, here I'll write it back up here, we have the absolute value of x is less than 1. So that tells me that if the absolute value of x is less than 1, then this value here is positive already. 1 minus x will be positive because the absolute value of x is less than 1. So then this difference here is positive. So I don't really need the absolute value bars. So let me get rid of them. Okay. So this is equal to all of this. If I multiply or divide both sides by -1, this is what I get, folks. The natural log of 1 minus x is equal to -x minus x squared over 2 minus x cubed over 3 minus etc. Okay, let's see if you and I can write this right-hand side in summation notation. So then this is equal to, notice that every single term is negative, every single term. So then it is the summation of, let's see, x to the power of k over k. But the whole thing is, every single term is negative, no matter what. So I can just put a -1 or a negative sign out here as k goes from 1 to infinity. Matter of fact, I can write this better. I can write this as the negation on the outside of the summation of x to the power of k over k as k goes from 1 to infinity. So what you and I were able to do is you and I were able to integrate our power series, and we got a new function that is represented by some new power series. Okay? So this is really great. You know what we should do? So what we have so far is that this is true for this interval of convergence. See if I can write it. There we go. Like that. So we should test the endpoints. So shall we? Let's test the endpoints. Let's plug in -1. Remember, this is written like this, or can be written like this. Okay. All right. So what I'm going to do is I'm going to plug in the endpoints to see if the power series converges at -1, whether the power series converges at 1. All right. Let's start with -1. Okay, when I plug in -1 into my power series, this is what I get. And we've seen this before. This is the convergent alternating harmonic series. So -1 is absolutely included in the interval of convergence. Let's check out +1. When I plug in 1, I just get the harmonic series. Well, I get a negative multiple of the divergent harmonic series. Multiplying the harmonic series by -1, doesn't change the fact that it's divergent. All right, so then in conclusion, this is what we have, folks.